EDX Core Pure, Matrices 5, Matrices and Simultaneous Equations. 3 simultaneous equations which have no unique solution. When you solve simultaneous equations in 3 dimensions, there are 5 possibilities as for how 3 distinct planes can be arranged. What do you think they are? Feel free to pause the video and see if you can sketch these different solutions, perhaps using 3 different sheets of paper. If the matrix M is the zero matrix, then all points are mapped to the origin and there is no solution, and that is a completely trivial case. If the determinant of M is not zero, there will be a unique solution because M is a non-singular matrix and the inverse does exist. The 3 planes in question will have a single common point, as we can see here. If the determinant of M is 0, there is no unique solution. M is a singular matrix and no inverse exists. There may be an infinite number of solutions where the equations are consistent. And here we have the 3 planes share a line of common points. So here the 3 equations are consistent and there is a common line. Finding the equation of that line is beyond the scope of the syllabus that we are studying. There may be no solutions and the equations are inconsistent. So there are 3 possibilities here. All 3 planes are parallel and distinct, which is the first diagram. 2 planes are parallel and distinct, crossed by a 3rd plane, which is the second diagram. Or we have a triangular prism in the 3rd diagram. Distinguishing between the different cases. When we look at the vector equations of planes in more detail, we will find that the coefficients of x, y and z for each plane represent a normal vector. So in the first diagram, where we have 3 parallel planes, we would see that all 3 normal vectors were parallel and therefore they would all be pointing in a direction normal to the 3 planes at the same time. In the diagram underneath, we would find that 2 of the normal vectors were indeed parallel, and we look for those normal vectors by seeing the coefficients of x, y and z. In the case of the sheaf, which is the top right diagram, the equations are consistent with each other and there is an infinite line of solutions where they meet each other, but finding the equation of that line, that common line, is beyond the scope of the syllabus that we are covering. And in the 4th case, none of the normal vectors would be parallel and these 3 equations would be inconsistent to each other and we have them forming a prism. And in a moment we're going to look at a GeoGebra file to look at 1 or 2 of these situations in a bit more detail. So here we have our 3 planes. 3x plus 2y plus z is 2, 5x plus 3y plus 4z equals 1, and x plus y plus 4z equals 5. And at the moment these 3 planes will meet at a unique common point. It's worth noting that if we look at this first plane, the coefficients of x, y, z will represent a normal vector of that plane. So 3, 2, 1 is a vector normal to plane 1, 5, 3, 4 is a vector normal to plane 2, and 1, 1, 4 is a vector normal to plane 3. So the first thing I want to do is I'm going to change plane 1. I'm going to change the coefficients to 1, 1, 4 and just watch what happens on the diagram when it becomes 1x plus 1y plus 4z. And you can see clearly now that we have 2 parallel planes. And the reason we have 2 parallel planes is because the normal vector to plane 1 is 1, 1, 4 and the normal vector to plane 3 is also 1, 1, 4. So both plane 1 and plane 3 have the same normal vector and therefore they must be parallel to each other, and the 3rd plane is slicing through them. So they are inconsistent with each other, and there is no solution to these three simultaneous equations. If I now change the first equation of the plane to 420, and we'll watch what happens. So the determinant of the matrix would be 0. You can see now that we've created a prism of matrices that are inconsistent with each other, and none of the normal vectors are parallel. So we've got three inconsistent equations with none of the normal vectors in the same direction. And that brings us to the end of matrices and simultaneous equations.